right, so let's work a problem. We've got ethane burns completely with 20% excess air. And in my diagram here, I've got a 1.2 in front of the A sub TH to account for that 20% excess air. So it's 20% excess air, in other words, 120% theoretical air. The products exit at atmospheric pressure. At what temperature does the water vapor in the products condense at? So I'm looking for the dew point temperature of the water vapor in the products, and I can assume that those products exit as an ideal gas mixture. So let's see, here's my equation for my dew point temperature. I know it's the saturation temperature at the partial pressure of that water vapor in my products. And since I'm assuming the products exit as an ideal gas mixture, I can use the combination of the ideal gas law and Dalton's model to relate the mole fraction of the water vapor to the partial pressure of the water vapor. The reason I want to do this is because I can get that mole fraction from the balanced equation, the balanced chemical equation for this combustion reaction. So the number of moles of water vapor in my products is just going to be Y when I solve for this equation here, and the number of moles in my mixture for the products is going to be X plus Y plus Z plus W. So I've got my balance, or I've got my governing equation. I'm ready to go. All right, so here's my fill in the blank answer. Here's my balanced equation, or soon to be balanced equation. And the first thing I need to do, I've got 120% theoretical air. So I need to solve for what is that theoretical air? What's the minimum amount of air that's necessary in a combustion reaction with C2H6 to burn that C2H6 completely all the way to CO2 and H2O, convert all the carbon to CO2, all the hydrogen to H2O. And that requires me to solve this equation right here. So this is the burning of C2H6 with 100% theoretical dry air and converting everything. I'll have CO2, H2O, and then nitrogen, because I've got nitrogen that's, I've got a lot of it in my dry air, and it's just kind of along for the ride. Okay, so if I do my mass balance, for the carbon, I've got 2 on the left-hand side. I've got X on the right-hand side. For my hydrogen, I've got 6 on the left-hand side. I've got 2Y on the right-hand side. And for my oxygen, I've got 2 times the theoretical amount of air. And then on the right-hand side, I've got 2X plus Y. So my Y is in the H2O. And since I know X and Y, I could solve for the theoretical amount of air. Now I could stop right here. I do not need, well, not stop the whole problem, but I can stop balancing this equation. I don't even need to plug anything in for Z, because I'm not interested in what Z would be for this equation. I'm interested in what it would be for the combustion of 120% theoretical air with ethane. So the only thing I was after here was calculating what A sub TH is. So that's 3.5, and I'm going to replace the theoretical air, A sub TH, in that top equation. And now I'm ready to solve for X, Y, Z, and W. So I'm not going to forget the W because I do have excess air. If I didn't have excess air, if I didn't have excess air like the case just a second ago where I was solving for the theoretical air, I wouldn't have any oxygen in my products. But I do have excess air, so I have oxygen in my products. Okay, so if I do my mass balance, the carbon hasn't really changed. 2 on the left-hand side, X on the right-hand side. Hydrogen hasn't changed. 6 on the left-hand side, 2Y on the right-hand side. Oxygen absolutely has. So I've got 1.2 times 3.5. Then I've got a subscript 2 on that oxygen term, so I'm multiplying everything by 2 on the left-hand side. And on the right-hand side, I've got 2X plus Y, and then I've got 2W. So that's my oxygen on the very last term right there. And so I get a W of 0.7. And then for nitrogen, I do need to solve for that here. So I've got a lot of terms on the left-hand side. Well, a lot of numbers on the left-hand side. I got 2, the subscript 2. So 2 times 1.2 times 3.5 times 3.76. And on the right-hand side, I've got 2Z. So now I've got my balanced equation. Now I'm ready to go back to my governing equation and plug in X, Y, Z, and W. So the partial pressure of my water vapor, I went ahead and put the ATM in terms of bar, just because your saturated water tables are in bar. And if I plugged in all those numbers, I get a partial pressure of about 0.14145 bar. and the saturation temperature at that partial pressure is about 51.7 degrees Celsius. So that's your answer. The water vapor in your ideal gas mixture of the products, your water vapor in the products is going to condense if you cool it, if it's cool below 51.7 degrees Celsius. All right, well, I hope that was helpful. Thank you for watching.